Let's explore the VI characteristics of a solar cell. We've already seen solar cells are PN junctions that convert light into electricity. And the way it works is when you shine light on a PN junction, the photons that are absorbed in the depletion region cause electron-hole pairs to be formed. And before they have time to recombine, electrons get accelerated towards the N side, holes get accelerated towards the P side. As a result, we have electrons being accumulated on this side, causing a negative charge on this side. Holes get accumulated over here, causing a positive charge on this side. And as a result, a potential difference is created. This is how solar cells convert light into voltage, photovoltaic effect. And we have talked about this in detail in our previous videos on Introduction to Solar Cells, working principles. So if you need more clarity, feel free to go back and check those out. But what we want to do over here is draw an IV characteristics. So let's go ahead and do that. So I'm going to do I along the y-axis, I draw V along the x-axis, and let's try and figure this out. Now, because over here solar cells themselves act like a battery, we need to be a little bit careful. I used to find this very tricky, so let's do this slowly. The way I like to start is by thinking about open circuit. Let's start by not attaching anything, okay? What's going to happen to the voltage as I keep shining light on it? That's what we want to think about. We know that as we shine light, more and more electron-hole pairs are formed, and they get accumulated more and more over here. And as a result, the voltage keeps increasing. But my question is, if I don't attach anything over here and I keep on shining light, would the voltage keep on increasing forever? Because more and more electron-hole pair holes will get accumulated. Will it never stop? Will it keep on increasing? I want you to pause the video and think a little bit about it. What do you think is going to happen eventually? All right. Now, as we shine light, more and more electron-hole pairs are continuously generated and continuously swept. And so they are continuously accumulated. But what's important to understand is that as more and more holes get accumulated on this side, it becomes harder for further more holes to come over here because these holes will start repelling these holes. And the same thing's going to happen over here. As more and more electrons get accumulated, it becomes harder and harder for even more electrons to get accumulated. They go slower. Think of it as they become slower and slower and slower, slower and slower and slower. Eventually, there'll come a point where so many holes are accumulated over here that when this hole tries to go over here, it gets repelled completely and comes back. Similarly, when this electron tries to go over there, it gets repelled and turns back. And as a result, these electron holes will come back to the depletion region. They will destroy each other. And so we'll reach a point where there are so much of accumulated charges that electron holes are no longer able to get swept. And so they basically will come back and keep destroying. And so we have now reached a point, another equilibrium point, where the voltage will no longer increase. We have now reached a maximum voltage, right? And so we're going to start plotting. Let's plot that over here. So where should I plot this? I know at this stage, current is 0. So on the current axis, we're going to get 0. And I have some voltage, in fact, maximum voltage. But is that voltage positive or negative? Well, remember, P is positive. When P is connected to positive, we call this forward bias. And forward bias is taken as a positive voltage, right? So our graph is going to be positive voltage, but 0 current. So it's going to be somewhere over here, right? And we call this voltage of open circuit, OC, because there is no circuit over here, this is open. And this is the maximum voltage you can ever get. And what does this voltage really depend on? Does it depend upon the intensity of light? Well, sure it does, but not much. You can see even if I increase the intensity of light or decrease the intensity of light, after that saturation has reached, no more electron-hole pairs will be able to be swept across, right? With more light, I will get more electron-hole pairs, sure, but they will still just come back and recombine. So this value doesn't depend much on light, but this depends on the construction actually. If I make this longer, I will be able to accumulate even more charges and have even more voltage. So anyways, this is our open circuit voltage. Now let's think about what happens when we close this circuit. And here what I like to do is start by thinking about a short circuit. So no resistance. So let's say we completely short it. Okay, again, what do you think is going to happen? There is a path now, and there is no resistance. Can you pause the video and think about what's going to happen and try to plot this point again on this circuit, on this graph. So pause the video and give this a try. All right. So now because there's a path available and there's absolutely no resistance, all these accumulated electrons, there's no reason for them to stay accumulated. All of those accumulated electrons will start flowing through this wire, and they will start destroying, or not destroying, think of it, yeah, destroying, yeah, and recombining with the holes over here. And so all the holes will be gone. And we'll now reach a point where for every electron and hole that is formed, the moment an electron hole is formed, they experience no repulsion anymore because there are no accumulated charges anymore. And as a result, they are freely, they're able to freely go through. And so I'll now have a very high current. And guess what? Because no more accumulated charges, no more voltage. So there'll be no potential difference across the two ends. Does that make sense? Well, if you think about it, it kind of makes sense, right? Because we know in a short circuit, because there is no resistance, there cannot be a potential difference across it. But logically also now, hopefully it makes sense that because there are no accumulated charges, there will be no potential difference now. So at this point in a short circuit, we'll have zero voltage and we'll have a very high current. So the question now is this a positive current or a negative current? Remember, our forward current is taken as positive, and forward current is from P to N. Which direction is this current? Well, electrons are flowing from P to N, meaning the current is in the opposite direction. So the current is this way. Inside, the current direction is from N to P. And so this is a negative current. So let's plot that on the graph now. We have zero voltage, but we'll have a negative current. So it'll be somewhere over here. And this is what we call the short circuit current. And again, this will be the maximum current I can ever get. The reason for that is because this is the only possible case where I have no accumulated charges, so no repulsion, and because of that, I get the maximum, maximum current over here. All right, what does this current depend on? Well, this current purely depends on the amount of light that is falling. Think about it. If 100 photons are being absorbed, I will have 100 electron pairs being created per second, and I'll have 100 electrons flowing over here per second. If I double that number, automatically this number will double. And so the current is completely governed by light. If I double the light intensity, this current will increase. If I get rid of that light, the current will go to zero. There'll be no current. Makes sense, right? Okay, now let's think about what happens in between. You can kind of think that the graph has to go from here to here, but let's try to do this logically. If I want to get a case in between, I need to consider a resistance somewhere in between. This was open circuit, infinite resistance. This is short circuit, zero resistance. So let's try to put in some resistance now, non-zero resistance. So let's say I put in a very tiny resistance over here. Very tiny. So I'm going to show it this way, very tiny resistance. What's going to happen? Again, I want you to pause first and think a little bit about this. All right, let's see. Now, since there is some resistance over here, when current flows through a resistance, or at least think of it this way, for current to flow through a resistance, there needs to be a potential difference. And how do we get a potential difference here? The potential difference can only happen if there are some accumulated charges, right? So now what's going to happen? To push the current through this resistance, some electrons will get accumulated over here, some holes will get accumulated over here. That will provide the required potential difference. And now once the potential difference is established, current can keep flowing. And notice, because there are some accumulated charges, these electrons will experience some repulsion, these holes will experience some repulsion, and immediately as a result, you can now see the current will reduce a little bit. So the current now is going to be a little less than the short circuit current. And now we have some positive voltage. So if you want to plot this, where would it be? I have some positive voltage, very little. I have current which is little less than the short circuit current. So it's going to be somewhere over here. And so my graph is going to look somewhat over here. All right, what if I increase that resistance a little bit more? So I'm going to increase that resistance a little bit more. What's going to happen? If I have more resistance, I require more voltage to pass current through it. And so to get more voltage, more charges get accumulated. The potential difference increases even more. And as the potential difference increases, the repulsion increases. And as a result, the charges slow down, they start slowing down. And so what happens to my current? The current reduces even more. So you can see where we're going with this. As I increase the resistance, the voltage starts increasing, the current starts reducing. And so hopefully you can now see what happens to our graph. The graph is going to look somewhat like this. So this is the graph of the solar cell. Before we conclude, I just want to go a little bit beyond just this quadrant, this fourth quadrant, because this will help us look at the photodiodes in general, bigger picture we'll get to see. So let's come back to this point, the short circuit. So let me just get rid of this and put a short circuit over here. Let's get rid of all of this. Remember what happened in short circuit? In short circuit, we said there's not going to be zero voltage. There'll be no voltage whatsoever. And all the electron holes that are formed immediately start flowing, giving us a maximum current, right? Okay, what if I want to go beyond this point? What if I want to go towards the left? How do I do that? I need to somehow put a negative voltage. There's no way I can get a negative voltage on a solar cell. So a solar cell can't do that. But what if I attach a battery and reverse bias it? Then I will get a negative voltage, right? And now if I do that, I will still keep getting the same current because the current purely depends upon light. And so if I go beyond this, I'll keep getting the same current. And you may have seen this before. This is our photodiode. Now, in this region, this is acting like a photodiode. I have reverse biased it, and I'm getting that same maximum current. All right, how do I go beyond this point? Well, to go beyond this point, I need to get a positive current. There's no way my solar cell can give me a positive current. To do that, I have to forward bias my diode by adding a battery. So if I do that, I add a positive here, negative here. And if I do that, I will now forward bias and I'll start getting a positive current. And if I do that, I'll get a forward current. It looks like this. Does this graph look familiar to you? It should, because this looks very similar to the normal PN junction graph, VI characteristics that we have seen before. Only difference is it was upwards. So the normal PN graph was somewhat like this. At 0 voltage, I get 0 current. And then this is what we got. So notice this means when you shine light on a PN junction, you shift that entire graph down. The more light you shine, the more you shift it down.